All right, welcome back to linear algebra. We're going to finish up section 2.5 on changing coordinates. Just want to review that theorem 2.23 about changing the matrix of a linear transformation from one ordered basis to another, representing it in one ordered basis to another. I want to do a couple of examples to illustrate how this stuff looks in specific settings. And then I want to just kind of talk about theorem 2.23 in the specific case where the linear transformation is left multiplication by a matrix in the standard basis, see what that looks like. And then we'll end just with some terminology about how these matrices are related. The matrices of a linear transformation and different bases are so-called similar. So I'm going to tell you what I mean by similar matrices. I'll give you a little exercise with them. Okay, let's start by recalling theorem 2.23. Theorem 2.23 said that if you have a linear transformation, a linear operator on a vector space, and you're given a couple of ordered bases, beta and gamma, if you let Q be the change of basis matrix from gamma to beta, so it changes gamma coordinates into beta coordinates, then the matrix of T in the gamma basis is given by this product, Q inverse times the matrix of T in the beta basis times Q. Okay, and I kind of wanted to give you a little bit of, I don't know, a way to kind of how to remember this formula. Why is it Q inverse T beta Q and not the other way around? So you got to kind of think about it in terms of like, well, what would you feed both sides of this equation, right? If you were going to say left multiply the matrix T sub gamma by a coordinate vector, well, that coordinate vector would have to be in the gamma basis, right? That's how it would make sense. The matrix of T in the gamma basis needs coordinate vectors in the gamma basis. So if you're going to left multiply something over on the left-hand side by that, well, the right-hand side has to be the same, right? So this is how I personally remember it, is that Q, remember, Q changes coordinate vectors from gamma to beta. So when you feed that vector into this first factor over here, the rightmost factor, it's going to convert the coordinates from gamma to beta, okay? And then what is T going to do? Well, T is going to take vectors in the beta basis and produce vectors in the beta basis because it's the matrix in the beta basis, right? And then what does Q inverse do? Well, Q inverse takes beta basis vectors and converts them into gamma basis coordinate vectors. So if you think about the right-hand side of this thing, if we kind of write out what they take, this thing will take a gamma vector and produce a beta vector. Okay, T then takes a beta vector and produces a beta vector. Q inverse takes a beta vector and produces a gamma vector. I mean, coordinates everywhere. So that's kind of how I remember what the order on the right-hand side is that the right-hand side needs to start with a vector in gamma coordinates. So this can't be a Q inverse over there because a Q inverse goes from beta to gamma. We need to start with gamma to beta. Okay, well, I hope that's helpful. Anyway, didn't sound that great as it was coming out. Let's look at an example. I'm going to kind of recycle an example from last time. Same thing, I'm going to just take vector space to be the plane, take beta to be the standard basis, and take gamma to be that basis of W's 1, 1, minus 1, minus 1. And then I'm just going to define a function t by writing coordinate functions for it. So there's my linear transformation, my linear operator on the plane. Okay, we already worked out last time that the coordinate change matrix from gamma to beta is this thing. You know, it's worth remarking that when you're changing coordinates from some basis, gamma, to the standard basis, well, the columns of Q are just going to be the gamma basis vectors stacked as columns. It'll always be that way in the coordinates, in the vector spaces Rn. We already wrote down Q inverse last time, so here it is again. And then what's the matrix of T with respect to the standard basis? Well, it's the matrix rows, I'll read them, 3, minus 1, 1, 1. How do I compute that matrix? Well, I just take T of each one of the basis vectors, applying using the formula. I see a T of E1 is 3E1 plus E2. That's where I got my first column. T of E2 is minus E1 plus E2. That's where I got my second column. So you can stop the video and verify that. And now I want to use theorem 2.23. Theorem 2.23 says that if you want the matrix of T in the gamma basis, I just sandwich the matrix of T in the beta basis in between Q inverse and Q in that order. Okay, I'll let you check my matrix multiplication here. I get the matrix 2, 0, minus 2, 2. So what is that matrix? That's the matrix I would left multiply gamma coordinate vectors by to get the gamma coordinates of the image under T. All right, we can verify that if you want. We can check it. Remember, W1 and W2 were given by those things. So you can just use the expression for T above to compute T of W1 and T of W2, and then check it out. I'll just let you verify that 2, 2, that row vector, well, that's two W1s plus no W2s. So that's why this first column would be that. And you can also check that negative 4, 0 is minus 2 W1s plus 2 W2s. So that explains this second column. But I'm just checking it by doing that, right? I got that matrix by using theorem 2.23. Cool. So if I wanted to perform the vector transformation, the operator T, and I was working in the gamma coordinates, I would be left multiplying by that matrix. Very cool. Let's look at an example. The book talks a little bit about this. I haven't emphasized this, but like reflections through lines are linear transformations. And in the standard basis, it's actually pretty easy to write down the function that would reflect in the x-axis. If you wanted to reflect in the x-axis, you would just leave the x-coordinate alone and negate the y-coordinate, yeah? That would take a point like a comma b and send it to a comma minus b. That's a reflection in the x-axis. So why is that so easy to write down? Well, it's because it's in the x-axis, and that's one of the standard basis vector directions. So here I want to do something that's a little bit more interesting. How could I write down a function, a linear map T, that reflects the plane R2, not in the x-axis, but say in some other line, like the line y equals 2x? Yeah, the line has to go through the origin if I want this to be a linear transformation. So I'm taking the line y equals 2x, it goes through the origin, and I want to write down a function T that does that. Well, I'm going to kind of take advantage of the fact that it's easy to reflect in a line if one of your basis vectors is kind of in the direction of that line. So I'm not randomly, but I'm strategically picking this basis, W1 and W2. So W1 is the vector 1, 2, that's on the line. It's got the slope 2 from the origin. And then W2, I'm choosing to be perpendicular to it. Yeah, so I'm just sort of switching the x and y coordinates and negating one of them. So that vector W2 is perpendicular to that line, okay? And so if I take that base, I'm going to take two bases. Beta is the standard basis, like we've been doing this whole lecture. And then I'm going to let gamma be this basis W1 and W2, drawn in red in the picture. And for the same reason, it was easy to write down the transformation T, the reflection in the x-axis with respect to the standard basis. It's easy to write down the reflection in that blue line in the gamma basis, right? Because the reflection in the blue line, well, if you reflect in the blue line, it sends W1 to itself, right? So this reflection T of W1 is W1, so its coordinates are 1, 0. It reflects W2 to its opposite, right? W2 is perpendicular to the line, so T of W2 is no W1s minus W2. So that matrix is easy to write down just for the same reason that the reflection in the x-axis was easy to describe. Okay, I'll let you check, and like I said, when you're converting, you get the matrix that transforms coordinates in some basis to the standard basis. Its columns are just the coordinates of your new basis vectors in the standard basis. So the change of coordinates from gamma to beta, the matrix Q down here, I just take W1 and make it the first column of Q, take W2 and make it the second column of Q. That's special because beta is the standard basis, but it makes it quick work. And then using that fact, that unproven fact last time, I can write down Q inverse as that thing. Okay? So now what do I want? I want the matrix in the beta basis. I have it in the gamma basis. So I'm kind of not using the exact statement of theorem 2.23 because I'm going the other way. I want to convert from gamma to beta. So I just multiplied by Q and Q inverse on each side. So I've got Q, T gamma, Q inverse. And again, let's use my little mnemonic thing here. What kind of coordinates would the left-hand side take? Well, it would take beta coordinates, right? So this thing has to take beta coordinates. Well, Q inverse converts beta to gamma. So it's got to go Q inverse gamma Q. I'll let you check, stop the video and check it. If you have the matrix Q inverse, you have this matrix T gamma, you have Q, it multiplies out to give that thing. Okay, so that's the matrix of T in the standard basis. So what does that mean? If I wanted to apply T to a point in the plane, A comma B, its standard basis coordinates are A, B, right? So I just write it as a row vector. Beta is the standard basis. Well, if you can imagine over here, I don't want to write it because I don't want to be bad notes. If I put an AB right here, well, what I did, I'd get minus 3/5 times A plus 4/5 times B. That's what I'm writing in the first coordinate. Similarly for the second. All right, so we've achieved our goal. This is kind of a non-trivial math problem, but here's a function from the plane to the plane where A comma B is understood to be the point A comma B in the plane, usual standard basis coordinates. And if you apply that linear transformation, that's a reflection in the line y equals 2x. All right, so if you take some point in the plane and you apply, it's got a location A comma B, T of it is going to be the point that is exactly opposite that point across that blue line. Cool. Very cool problem. Okay. Let's specialize off a little bit here. If you start with an n by n matrix, start with a square matrix. Recall that we use this notation L sub A to denote the operator on the coordinate vector space Fn. L sub A of x is just A times x. It's a linear map, it's a linear operator. And you probably also recall that its matrix in the standard basis is just A. So here again, let me remind you that beta is the standard basis. Right, so the matrix of the left multiplication by A in the standard basis is the matrix A. is what that equation says. Okay, so if we apply theorem 2.23 or the sort of inverse version of it, theorem 2.23 exactly, that if you wanted to know the matrix of this transformation L sub A in the gamma basis, well, you just take your coordinate change matrix Q and you sandwich A in it in that order, Q inverse AQ. Okay, so that converts the matrix A into a square matrix, same size, n by n matrix, and that new square matrix would be the same left multiplication linear operators matrix in the new basis. Cool. Let's end with just some terminology. If you give me two square matrices, I'm going to say that one of them is similar to another. Here's the quantifier. If there exists an invertible matrix Q that satisfies that equation. Yeah? If B is Q inverse times A times Q, then I'm going to call A and B similar. So one way to kind of rephrase theorem 2.23 is that any two matrices for a given linear operator in two different ordered bases are similar. Okay, so that's what theorem 2.3 says, is that if you have two bases for a vector space, the matrices that represent a linear operator in those bases are similar. Cool. I'm going to leave this as an exercise to you, but similarity is an equivalence relation on the set of all matrices. So what do I mean by that? I mean that it's reflexive. So I'm going to ask you to check that it's a reflexive relation. Every square matrix is similar to itself. So you'll have to say what the Q is in the notation above. It's a symmetric relation. If A is similar to B, then B is similar to A. Okay, and it's a transitive relation. If A is similar to B and B is similar to C, then A is similar to C. So this Equivalence relation partitions the set of all square matrices into equivalence classes. And another interpretation of theorem 2.23 is that the matrices in an equivalence class all represent a single linear transformation from V to V. All right. So any linear transformation, it has a whole bunch of matrices and a bunch of different bases, but all those matrices are similar. So these equivalence classes are really the sort of essence. If you really want to study the linear operator, you're not going to, in terms of matrices, you're not really studying it in terms of any one specific matrix, but rather this equivalence class of matrices. Okay, I'm going to leave it there. Thanks for listening.